Welcome to Nasrobeta Engineering College, and this is Sesh Kumar, Assistant Professor in Department of ECE. And today I am going to explain a topic from PTSP subject, that is probability theory and stochastic process. And the topic which I have chosen to explain today is power spectral density. Power spectral density. Power spectral density, and this power spectral density can also be specified as small PSD, that is power spectral density. So in this we are going to have a spectrum. So in order to have any spectrum, compulsory it should be a frequency domain. So power spectral density will always be in a frequency domain. So here the signal which we need to consider is a frequency domain. So as it is a topic that is related to a PTSP, that is probability theory and stochastic process, here I am going to consider a random process, x of t. So x of t is a random process and it is a function of time. Always the random process is a function of time. So here as t is going to vary, the amplitude x is also be varying. Okay. So as it is a function of time, as t is continuously increasing or decreasing, or however if it is varying, then the amplitude of x of t will be varying. That is the random process. So x of t is a random process. So as we are going to discuss about the spectral density. So compulsory we need to have a frequency domain instead of a time domain. So for converting this time domain into a frequency domain, the thing which we are going to use is transformation techniques. And mostly in this we are going to use the Fourier transformation techniques. And we are provided with different types of transformation techniques, that is Laplace transforms, Jet transforms, Fourier transforms. So mostly in this we are going to use a Fourier transformation. And in order to apply this Fourier transform on this transformation x of t, if we want to apply the Fourier transform on the x of t, compulsory this x of t should possess the Dirichlet conditions. So if it satisfies the Dirichlet conditions, then only we are able to apply the Fourier transform on x of t. And as the random variable is not able to this random variable is unable to possess all the conditions of Dirichlet, so we cannot directly apply the Fourier transform on this random process x of t. So instead of directly applying this Fourier transform on x of t, we are going to consider the other variable, that is rxx of tau. Rxx of tau, and this rxx of tau is nothing but an autocorrelation function. Okay. So we are going to apply a Fourier transformation technique on autocorrelation function Rxx of tau. So this is the concept that is hidden in this power spectral density. And now let us define what is this power spectral density. And for this we are provided with two definitions. First let us discuss. Define the first definition. So these power spectral density, it can be represented as Sxx of omega. As we have said that compulsory it should be a frequency domain, so it should be a function of omega. So here I have considered Sxx of omega, and this Sxx of omega is nothing but a power spectral density notation. So coming to the definition, first as I have said that we are processed with the two definitions. Coming to the first definition, so that is the power spectral density PSD. So small PSD represents the power spectral density. So the power spectral density of a random variable x of t, the power spectral density of and here this random variable also compulsory it should be a white sense stationary. Power spectral density of a white sense stationary random variable x of t is defined as the Fourier transform of Rxx of tau, that is the autocorrelation function. So Sxx of omega can be obtained by implementing Fourier transform of Rxx of tau, that is autocorrelation function. The power spectral density of a wide sense stationary random process x of t can be defined as a Fourier transformation of autocorrelation function Rxx of tau. That is your first definition. So as per that first definition, we can represent this power spectral density as Sxx of omega is equal to integral minus infinite to infinite Rxx of tau e power minus j omega tau d tau. So this is the expression. So the definition can be expressed mathematically in this way, that is Sxx of omega is equal to integral minus infinite to infinite Rxx of tau e power minus j omega tau d tau. So from this we can obtain the power spectral density Sxx of omega. And if Sxx of omega is provided to us and we need to obtain Rxx of tau, then by implementing the inverse Fourier transformation technique, inverse Fourier transform of this function, we can obtain Rxx of tau. So how we can give this Rxx of tau means by applying the inverse Fourier transformation technique, that is Rxx of tau is equal to 1 by 2 pi integral minus infinite to infinite Sxx of omega e power j omega tau d omega. So in this way we can obtain the Rxx of tau, that is autocorrelation function, if a power spectral density is provided with us. Okay, so this is the first definition. And coming to the second definition, as we have said that x of t is a wide sense stationary random process, that is already defined. So for this, how we are going to have this power spectral density means Sxx of omega. So this Sxx of omega is nothing but the representation of the power spectral density. So this Sxx of omega can be given as limit t tends to infinite expected value of magnitude of x t of omega whole square by 2t. So this is the another definition, that is the another formula for this power spectral density. So Sxx of omega is equal to limit t tends to infinite expected value of magnitude of xt of omega whole square by 2t. And here what is this xt of omega means? It is the Fourier transform of xt of t. So on the Fourier transformation technique of xt of t, we are going to obtain the xt of omega. Okay, and this xt of t is the signal, as we have said that directly we cannot apply the Fourier transformation technique on x of t. So instead of x of t, I had considered the other random variable xt of t, and here xt of t is defined only in the time interval minus t to t rather than minus infinite to infinite. So here directly I am not implementing the Fourier transform on x of t. Instead we have considered xt of t. Okay, so these two are the formulas that are related to the power spectral density, and in this we are totally we can have three different formulas. This is one which is going to specify Sxx of omega, and the other is autocorrelation function, this is Rxx of tau, and the other formula is this one which is also going to represent the power spectral density Sxx of omega. So these are the definitions, and by using these definitions we are going to measure the average power of a random variable. Okay, average power of the random variable by using this power spectral density formulas. So let us derive the average power. So in order to find the average power, now I am going to assume a random variable x of t, and this x of t is defined only in the interval minus in t to plus t. So in as a suffix I am going to write it as xt of t. So this xt of t will be your x of t when t lies between minus t to plus t. Okay, so xt of t is a random variable that is defined only in the time interval minus t to t. So for that here I have represented that sentence in an equation form, that is xt of t is equal to x of t over the range t lies between minus t to t, and beyond this range, that is minus infinite to minus t as well as t to plus infinite. So xt of t signal is 0. xt of t signal is 0. Okay, so this is the generalized notation of a random variable which I had considered, xt of t. So this is xt of t, and now I am going to consider the Fourier transform of xt of t. So automatically the Fourier transform of xt of t will be equal to, it can be given as xt of omega. So the Fourier transform of this will be given as xt of omega is equal to integral minus infinite to infinite xt of t e power minus j omega t dt. Okay, so this is the generalized Fourier transformation technique. So Fourier transform x of omega is equal to integral minus infinite to infinite x of t e power minus j omega t dt, and instead of x of t we are having xt of t, and here the Fourier transform we have represented as xt of omega. Okay, and this can be given as because the signal xt of t is defined only in the range minus t to t, and in the other range it is 0. So instead of the limits minus infinite to infinite, we can represent it as minus t to t, because beyond this minus t and above this plus t we are going to have the value 0. So that values will be 0, and I am not representing this. So here this integration is split up into 3 parts, that is minus infinite to 0 one part, minus infinite to minus t one part, minus t to plus t second part, and plus t to plus infinite is the third part. First part and third part will be 0. So automatically we have to split second part, that is the integration limit from minus t to t. So minus t to t x of t. So instead of this xt of t we are writing x of t. So x of t e power minus j omega t dt. Okay, so this is xt of omega, and now we are going to have an average power of a random variable xt of t. So in order to have an average power, first we need to find the energy signal. And how we are going to have the energy signal means, if a signal is displayed twice, then we are going to have an energy signal. So instead of x of t, we are going to have x square of t for energy signal, and this energy signal is represented as E of t. E of t is the energy signal. So energy signal E of t is equal to integral minus t to t x square of t dt. Okay, x square of t dt, this is the energy signal, and for this energy signal I am going to represent the equivalent, and the energy signal here I can represent the time in time domain, but for the power spectral density, whatever it is, the spectral density should be always in a frequency domain. So now I need to convert this time domain into frequency domain, and here I cannot use directly the Fourier transformation techniques. So by using Pascal's theorem, I am going to convert this time function into a frequency function. So how I can have means, that is directly a Fourier transformation technique only, but there will be no exponential term. So 1 by 2 pi integral minus infinite to infinite x t of omega whole square d omega. Okay, so directly here I am having for converting this time domain into a frequency domain, Pascal's theorem I had used. What does this Pascal's theorem say means? It is almost similar to the Fourier transformation technique, but the exponential term will be missing. That is integral minus infinite to infinite x of t e power minus j omega t dt can be represented. That is the Fourier transformation technique. 1 by 2 pi integral minus infinite to infinite x of omega e power j omega tau d omega. So in this, and as here there is no exponential term, here also the exponential term will not be presented. Okay, so this is overall the representation, that is the conversion of a time domain signal into a frequency domain signal. So what is the frequency domain signal means? 1 by 2 pi integral minus infinite to infinite x t of omega whole square d omega. So this is the power signal. And now I am going to have the this is the energy signal, and from this energy signal now I am going to derive the power signal, and this power signal can be represented as P of t. P of t is the power signal, and this power signal is derived from the energy signal, which is divided by 2t. Okay, so if the energy signal is divided by twice the time interval, then it will be our power signal. So P of t is equal to E of t by 2t, when t is the time domain, as we have said that here minus t to t. So it is a time interval. So from this what we can write the power signal? So instead this one and this one I am going to divide with 2t. So here the equation which I am going to get is 1 by 2t integral minus t to t x square of t dt. This can be represented as 1 by 2 pi integral minus infinite to infinite x t of omega whole square by 2t d omega. So for this equation and for this equation I had divided these two equations with twice the time period, that is by 2t. So here for this from this expression here I had multiplied here by 2t, and from this expression for this value from here I had divided with 2t. Okay, so this is the power signal, but here we need to have the overall power signal, that is the average power signal, the average power. So here the power which we have considered is only in the interval minus t to t, that does not represent the overall power. So in order to have the overall power, that is the average power, for this power signal, and here this average power is represented as Pxx of Pxx. So here the Pxx means average power. So this average power can be represented as the limit t tends to infinite expected value of power signal. So if in order to obtain average power, if the limit t tends to infinite, the expected value of the power signal will give you the average power. So for this equation I am going to have the expected value as well as the limit t tends to infinite. So therefore Pxx is equal to limit t tends to infinite 1 by 2t integral minus t to t x. So here I am inserting the expected value. So E of x square of t dt. Okay. So from this equation I had added limit t tends to infinite as well as expected value of E of x square of t. So here E represents the expected value. So these two terms I have included in this equation, and similarly for this equation also I need to include both those two equations. So what does that represent means? 1 by 2 pi integral minus infinite to infinite. So here I am adding limit t tends to infinite T of omega whole square by 2t into d omega. Okay, so this is the overall average power signal. This is the power signal and this is the average power signal, and we need to find the average power signal, that is the power. For power spectral density, here the power specifies the average power of a random variable. So the average power of a random variable can be represented as Pxx, and this can be represented in two domains, in time domain as well as a frequency domain. So in time domain representation, this is the formula: limit t tends to infinite 1 by 2t integral minus t to t expected value of x square of t dt. And in time frequency domain, it is 1 by 2 pi integral minus infinite to infinite limit t tends to infinite expected value of magnitude of xt of omega whole square by 2t d omega. So these are the expressions, and after these, just a moment. So after these, we are going to substitute the formulas directly. That is Pxx is equal to, and the limit t tends to infinite 1 by 2t integral minus t to t x of t dt will give you the average time value. Okay, time average value. So limit t tends to infinite 1 by 2t integral minus t to t of any signal x of t can be represented as time average of x of t. Time average of x of t. So instead of here x of t, what we are provided means e of x square of t. So how we can represent means time average of e of x square of t. Time average of e of x square of t. So Pxx can be represented as, so from this what we can write in time domain, time average of e of a of expected value of x square of t. Okay, so this is one representation. And coming to the other representation, that is in a frequency domain. So in frequency domain, how we can give the average power spectrum in answer? So Pxx is equal to 1 by 2 pi integral minus infinite to infinite. And coming to this, the limit t tends to infinite expected value of magnitude of xt of omega whole square by 2t. All these terms can be represented as power spectral density. Already at the starting we had given the three equations. So first one is sxx of omega, second one is rxx of tau, and third one is again sxx of omega. And coming to the third equation which we have seen earlier, that is sxx of omega is equal to limit t tends to infinite expected value of magnitude of xt of omega whole square by 2t. Okay, so these values, this is the formula for sxx of omega. So directly here I am going to represent as sxx of omega d omega. So these are the two formulas for power spectral density, that is the average power spectral density. So the average power spectral density is given as the time average of expected value of a second moment. Okay, and expected value of x square of t can be represented as second moment. So this can be given as Pxx of average value of second moment. Okay, and similarly next one, Pxx is equal to 1 by 2 pi integral minus infinite to infinite sxx of omega d omega, and here sxx of omega is the power spectral density. So this is the concept, that is so this is the overall expression of power spectral density. Okay, so I think it is clear to all, and let us meet in the another session for discuss the other